Hello everyone, Earth.Otherwise here to continue our journey through game programming in C++ start to finish by Eric Yuzwa. Speed in collision detection is done the same way as when we were figuring out what to render and what doesn't need to be rendered. We've in fact already created basic collision detection when it comes to our camera with frustum culling. Now we're just going to be putting that into a specific set of functions to be used by anything with a physical body. So, create a new set of .h and .cpp files. I'm calling mine oCollision, but you should replace the O with the first letter of your game engine. Here, there will be 4 structs. I call mine oCallSPR, oCallAABB, oCallPlane, and oCallCNVX. These will be what defines sphere, bounding boxes, planes, and convex objects in the context of our game world. All of them, except the plane, will contain a GLM vec3 pointer to a position. Sphere will have a float radius, AABB will have a max and min offset, which are 2 GLM vec3s, plane will have a GLM vec3 normal and a float offset, as well as a constructor, which will set those two things. Convex will have a vector of planes, that's going to be called planes. There will be 6 functions, each returning a boolean. There's sphere-on-sphere collision, which takes a pair of sphere pointers, AABB collision, which takes a pair of AABBs, sphere plane side, which takes a sphere pointer and a plane pointer, sphere convex collision, which takes a pointer to a sphere and a pointer to a convex shape, AABB plane side, which takes a pointer to an AABB and a pointer to a plane. Finally, AABB convex, which takes a pointer to an AABB and a convex shape. These aren't being contained in a class right now. Later, we will probably contain all collision objects and functions inside of a collision class where it will all be taken care of. But for now, we're doing things fast and inefficient. Now into the .cpp file. First is sphere-to-sphere collision. This one is simple. If the length of the first position minus the second position is less than the combined length of the 2 radii, then we have collided. If not, then we haven't collided. Next is the AABB collisions. You'll have noticed that they aren't called boxes, but rather axis-aligned bounding boxes, or AABBs. In order for collision detection to be faster, we use a box aligned to the X, Y, and Z axes that encompass an object. You'll see why in a second. The code goes like this. If the position plus the maxed offset of the first box is less than the position plus the min offset of the second box, then we can't be touching. Then we check the reverse. If there's any space between the 2 boxes in the X, Y, or Z direction, then they can't be touching. But if there isn't any space, then they are touching. The way I do this means that non-collisions are much faster than collisions. Next is sphere plane side. This one is a bit different because we're just checking if the plane is completely on the wrong side of if the sphere is completely on the wrong side of the plane rather than if it is intersecting the plane. You'll remember that this is how we are currently doing frustum culling. You can and should double check your camera class for this equation. But we know that the dot product of the normal of the plane and the position of the sphere plus the plane's offset will give us a floating point value of where the sphere is relative to the plane. If that value is less than the inverse of the sphere's radius, then the sphere is on the quote-unquote outside of the plane, or it's negative offset from the plane. Next up is the sphere-to-convex shape. This is where it's important that we know which side of the plane things are on. Here we test the sphere against all of the planes, and if it's outside any of them, then it is not intersecting with the convex shape, which is made up of planes. You'll remember that this is how our frustum works. You'll also remember that all the normals of the planes must be pointing inward to work. Next is testing an AABB against a plane. First, we create 2 new vec3s called min and max relative to the plane. If the plane's normals are greater than 0, then the position plus the min and max relative to the plane remain the same. If not, then the min and max are switched because the plane is pointed in the negative direction rather than the positive direction, which means that since the boxes are set like minimum XYZ, maximum XYZ, you can see that if we're pointed so that the maximum XYZ is closer, then that is in fact the closer point rather than the further point. We do this for X, Y, and Z. In this way, we get the correct closest and furthest plane. Then, just like the sphere, we get the dot product of the closer point and the plane normal plus the plane offset. If that's greater than 0, then the box is on the quote-unquote inside of the plane. If not, we check the max relative to the plane. If that is greater than 0, then that is quote-unquote inside. If not, then the box is fully outside the plane. Now that I'm actually saying this out loud, I realize that we could literally just check the maximum value, and if that's positive, then that's fine. We don't need to check the minimum value at all. That's only useful if we're checking if the box is intersecting the plane. Finally, for this file, we'll do the same thing as the convex to sphere collision. Call the AABB collision for each of the planes in the convex shape. If none of them return false, then the AABB has indeed collided with our shape. Now, go into cameras and get rid of the old and now obsolete code, the plane struct and the checking for boxes and spheres in there. Now include our collision class. We don't need that plane class, as I mentioned. We also don't need the frustum boolean or vector of planes in our camera 3D. We also don't need isSphere and isBox in view, as I mentioned. Instead, we will have a function that will return a convex pointer called getFrustum that will return a reference to mFrustum, which will be a member variable of type oCallConvex, or CVNX. It should be CNVX. Now into the .cpp file of camera. Remove the functions that we got rid of in the .h file. Between initializing our receivers and our first update call, we're going to set the position of mFrustum to our position, and we're going to call createFrustum so that it's made when we first create the class. If we don't do this, and we're, for example, checking it before we've called update, like before we've moved, then everything will be invisible to our camera because the frustum won't exist. That'll actually probably create an error. Now we're going to make some changes to where our planes are stored. Instead of in mFrustum, which used to be a vector of planes, it is now in mFrustum.planes. Nothing else really needs to change here, I don't think. I'll double check it in a second. Now down to update. We're going to call createFrustum at the bottom of each of our movement ifs, including changing the camera rotation. That way we're only rebuilding the frustum if we've actually moved the camera. And that's it for the camera class. Now quickly into spatial scene graph oct.h, where we will include ocollision.h and make a member variable called oCallAABB with a function that returns a pointer to that AABB so that we can check if our scene graphs are in view. Also add a vec3 for the center of the cube. In the .cpp file, we simply set the center using our getCenter function, and then set the box's position to a reference to our mCenter variable that we just made. Follow that up by defining the max and min offsets by the glm vec3. Set that using the max and min values minus the center. And we have everything we need to check if our octs are in view. Looking at this class, though, we should really refactor it significantly, but that can be done later, most likely in an addendum to the series as a whole. Now we're going to quickly change something I should have done a long time ago, and what many of you may have already done, otherwise a lot of you probably haven't even been able to put more than like 4 or 5 cubes on the screen. Pop into ocube.h. Here we are going to change every reference to a string to a GLU int. The texture file paths and the vector of textures is where those are. We'll further include ocollision.h and an oCallAABB called mBox, or mBoundingBox if you will. We'll also have a function that will return a pointer to said box. In the .cpp file, we'll have to set the position of mBoundingBox to mPosition. mMax offset will be defined by half the side length, positive and negative. In Render Entity, we no longer need to load the PNGs and instead can simply supply the GLUINTs stored in our vector. It may behoove us later to change that from a vector to simply 6 GLUINTs, as it's kind of a pain to switch them out, like switch out a vector, but if they're just 6 individual like numbers, then that's fine. Or heck, even pointers to numbers, though I don't think we'll need to do that. I'm not sure, I'll check it out later. Now to make our changes in main and observe the results, or lack thereof. Include ocollision.h. Now scroll down to where the cubes are created. Right below them, call otherwise load PNG functions that were previously called an ocube, and pass those GLUINTs into the cube entities. Follow that up by changing the collision check from the previous camera collision checks to our new checks for AABB CNVX, providing the getBox and getFrustum functions from the scene graph octs and the cubes and the camera, respectively. We need to quickly pop into spatialentity.h to make a virtual getBox function so that we can call that when we are looking at our cubes when they're in a spatial entity stacked. That virtual version will return a null pointer. With that done, things should work just as they have before. I've changed how the cubes are placed a little to demonstrate. You might notice that the cubes seem to cut off at a certain point. This is the limit of the cube of cubes, not the frustum working incorrectly. Anyways, this has been Earth.Otherwise. I'll see you next time.